Welcome back to Applied Mathematics. In this video, I want to introduce you to the coordinate plane. Before we get there, I think it's only reasonable that we start off with some motivation. Why are we going to be working with this tool called the coordinate plane? What is it good for? So let me get my head out of the way, and we're going to start off this video with an equation in two variables. Which does kind of what it sounds like it's going to do. It's going to be an equation. It's going to have an x in it. It's also going to have another variable, y, in it. And an equation in two variables can be as simple or as complicated as you would like it to be. For our purposes this semester, we're going to lean on the simpler side. We're going to kind of avoid the more complicated sides. And focus on a linear equation in two variables. A linear equation in two variables is any equation which can be written in the form ax plus by equals c. We talked earlier in this course about linear equations in one variable, which were any equation that could be written in the form ax plus b equals c. So the only real difference is we've now inserted this y variable. When we had a linear equation in one variable, a solution to the equation was a value we could plug in for x in order to get a true equation. Now that we have a linear equation in two variables, we're going to need a solution is a pair of values x and y together. So if you plug this particular x in and this particular y in, you will get a solution. It's going to turn out that there tends to be infinitely many solutions to linear equations in two variables. Now, when we dealt with equations in one variable, when there were infinitely many solutions, the solution was honestly kind of boring, right? Everything is a solution. It's not that dire for an equation in two variables. If we have some pairs of x and y that satisfy the equation and other pairs of x and y that do not, the pattern of when these x and y's satisfy the equation is something that's still interesting to analyze, even though there are infinitely many solutions. Let's stop talking in generalities and put some specific examples out here. So, for example, the equation 5x plus 4y is equal to 40. If I plug in that x is equal to 4 and y is equal to 5, then I will get 5 times 4 plus 4 times 5, which is 20 plus 20, which is in fact 40. Exactly what the equation said I was going to get. If I plug in x equals 8, y equals 0. I get 5 times 8 plus 4 times 0. Which once again is a perfectly valid solution. If I plug in x equals 2 and y equals 7, though, I get 38 on the left-hand side, which is not the same as the 40 I have on the right-hand side. This is not a solution. So, we have a situation where some points, some ordered pairs x and y are solutions and some are not. And we want to be able to categorize them, classify them, and describe them. That's what the coordinate plane is good for. The coordinate plane starts with a number line. I'm going to label this number line as x. I'm going to make sure to put 0 in the middle, although I'm not going to label 0 for reasons that will become apparent in just a moment. And I'll put the positive numbers to the right. I'll put the negative numbers to the left. Normal, everyday number line. I am then going to draw a second number line vertically right through the point where x is equal to 0. I'm going to call this number line y. I'm going to put the positive numbers going upward and the negative numbers going downward, and putting the y equals 0 right on top of the x equals 0. We're going to call this point where x and y are both equal to 0 the origin. All right, the origin is the point where x is equal to 0 and y is equal to 0. We're going to call this horizontal number line the x-axis. We're going to call this vertical number line the y-axis. The next thing we're going to do is we're going to notice that the two axes divide the plane into 4 regions. We're going to call those regions the quadrants. We're going to start off with this region in the top right and call it quadrant 1. Before we do anything else, let's think for a moment about why this is quadrant 1. Well, this is the region that has positive values for the x-axis and also positive values for the y-axis. There are a ton of applications of equations in 2 variables where only positive numbers really make sense. For example, the x-axis might be measuring how long a ball has been rolling down the hill. The y-axis might be measuring how far has the ball rolled. Well, if you're measuring time, you're going to start with some 0 point and continue from there in a positive sense. If you're measuring a distance, you're going to start from some 0 point and measure from there in a positive sense. You're going to stay in the positive values for x and y for the entire time that you are watching this ball roll down the hill. So in that application, we only need the first quadrant and we leave the rest of the graph off. That is incredibly common. Right? Most applications, not all of them, but most applications that you'll see after you leave this course are going to focus on just that first quadrant. So we're going to draw our axes like that. Then from here, this is where things get kind of interesting. And it's particularly challenging to me because I'm in mirror mode. You can't tell, but this is my left hand and it looks like it's my right hand to you. And that's important. You want to be using your right hand. So forgive me as I'm very clumsy here because this is backwards. But there is a right hand rule. If you take your right hand and you place it at the origin with your thumb facing up, your fingers curl from quadrant 1 to 2, 3, and 4. We number the quadrants in that order. The right-hand rule governs a ton of the things that you come across when you are looking at graphical analysis of anything in mathematics. Another way of phrasing a simple idea that you have probably had drilled into your head. Lefty-loosey, righty-tighty. How do you tighten a screw or a bolt? Another way to think about the same rule is take your right hand, point your thumb in the direction you want the screw to go. If you want the screw to go into the wall, you point your hand that way. And your fingers curl to tell you how to drive the screw. If you want the screw to come out of the wall, you point your thumb that way, and your fingers curl to tell you how to drive the screw. That idea of using your right hand and the way your fingers on your right hand curl is foundational to a ton of stuff in the geometric analysis of mathematics, in graphing, in a lot of things that we don't have enough time to talk about this semester, but you may be looking forward to in a future course. I apologize to any of the lefties out there, but when these rules were being established, unfortunately, it was a time in society where being left-handed was considered a sign of being possessed by a demon, and if you were able to use your left hand as your dominant hand, you were most likely going to be locked into a tower and promptly forgotten about. All right. Before I move on too much further, I want to go ahead and name this. The coordinate plane that I've been describing here is more properly known as the rectangular coordinate system, because when you look at how the axes interact with each other, it's going to form a bunch of rectangles. There are other coordinate systems. If you continue onward long enough, the next one you're going to come across is what's known as the polar coordinate system, which is all about angle. Polar coordinates are a very powerful tool, but that power comes with the cost of making them more difficult to work with, so we stick with rectangular for a while to make sure you're really comfortable with the foundations first. The name Cartesian coordinates has fallen out of favor in the past 10, 20 years, but up until about 20 years ago, it was the only name that was given to this system. And the Cartesian coordinates are another name for the same thing. They take their name from the French philosopher René Descartes. of I think, therefore I am fame. As the legend tells us, René Descartes was terribly ill. He was bedridden, and he was laying in his bed just staring at the ceiling. The ceiling had a hammered copper tiling pattern on it, so it was arranged in a bunch of squares. There was a fly buzzing around and driving René Descartes absolutely mad. And he was trying to tell the servant who was taking care of him where the fly was so that the servant could get rid of the fly and René Descartes could go back to resting peacefully and trying to recover from his illness. He realized that if you count across some number of tiles and count up some number of tiles, it's a way to uniquely get you to a particular point on the grid of the ceiling tiles. He fleshed out that idea a little bit and invented the concept of graphing equations. René Descartes did more to advance the study of mathematics while stuck in bed sick than I have any hope of doing in my entire life. But we benefit from what he has done and we can use it to our advantage. Let's go back to that equation that I was looking at earlier. (5x plus 4y equals 20). We had already established that when x is 4 and y is 5, we have a solution. And when x is 8 and y is 0, we have a solution. Let's look for one more. In order to find a solution to an equation in two variables, we are generally going to pick a value for one of the variables. It doesn't matter which variable we pick, and it doesn't matter which value we pick, but some values are going to make your life a little bit easier. Let's pick x equals 0. We then plug that value into the equation and solve for the other variable. Why is this making no sense? Because I wrote the wrong equation down. The equation we had earlier was 5x plus 4y equals 40, and these are in fact solutions to that equation. And once I have the correct equation written down here, we can solve that. We plug in 0 for x, we start arranging solving for y. I get, in this case, that y is 10. I can plot these solutions on the coordinate plane. I've got a bunch of positive numbers, so I'm going to greatly exaggerate the first quadrant. I also don't want to spend forever numbering things, so you can see that I've numbered every other tick mark here instead of numbering every tick mark. I'm going to go ahead and plot my points when x is 4 and y is 5. That takes us to the point right here, right? So I find x is 4 on my x-axis, I find y is 5 on my y-axis, I bring those together, and I get the point that's right there on my coordinate plane. When x is 8, y is 0. That's the point down here. When x is 0, y is 10. That's the point up here. I do my best to play a game of connect the dots, and I get a solution. Every linear equation has a graph that forms a straight line. This isn't true of every equation, but it is true of every linear equation. That's why we call it that. Linear equations produce lines. So knowing that helps us tremendously here. We know that if we have 2 points, that uniquely defines a line, but it's difficult to sketch the points as clearly as you may want to, so sometimes it's worthwhile to put in an extra point. Right? 2 points makes a line, 3 points makes a slightly straighter line. It's also important to remember that the line continues, right? The points that we happened to pick are not endpoints. The line continues beyond this point, which is why I drew it beyond there, and I put an arrowhead to indicate that it keeps going. And that is the process of graphing a linear equation. Before I wrap up on this video, I want to change gears and look at the elephant in the room. There is software that does this for us. Computers are actually really good at graphing. I am on a website called Desmos, desmos.com. This website is free to anyone, no strings attached. Go to desmos.com, click the button that says Start Calculating. It brings you to this screen. You can start doing stuff. Right above my head, I'm going to get my head out of the way so I can do this, is a place where I can type in an equation. So let me do just that. Let's type in the equation 5x plus 4y. How about typing in using correct letters? 5x plus 4y equals 40. That's the equation we were trying to graph. And it currently falls off the edge of the screen, but there's a nice zoom out button over here, which will give us a nicer picture and let us see the same line that I just plotted by hand. Before I bring my head back up, I want to point out a couple of things. First of all, this button down here for Show Keyboard. This brings up some notational guides. If you're using a tablet, this makes it easier to find your X and Y without having to find your own keyboard. It will allow you to type in square roots, the pi symbol. There's a pretty extensive library of functions here, none of which we're going to be needing in this course, but I wanted to mention that it was all there. So if you are working with this in a future course, those will probably come in handy. The other thing I wanted to mention was over here, the Share Graph button. This allows you to print a copy of your graph or export your graph as an image. Exporting your graph as an image allows you to save it to somewhere that you can work with it later, such as uploading as part of a take-home project for this course. All right, so if I can use computer software and it will draw a graph for me without much of any effort whatsoever, what's the value in being able to draw a graph by hand? Well, I hate to bring it down to it's a learning tool, but that's really what it is. There are times when sketching a graph by hand can help you out, can help you understand how a equation is behaving, how a project is behaving. But for the most part, sketching graphs by hand helps you to learn to relate the graph to the equation. You start to get a better sense of what the features in the graph actually represent in the equation, And that's the point. Right? The point of graphing is not to take an equation and turn it into a picture. The point of graphing is to take a picture and turn it into some new piece of information about the equation you are studying, how that equation relates to the world, how that equation relates to the problem you're trying to solve. In the next several videos, I'm going to be looking at those questions in more depth. In this video, I just wanted to get you familiar with the basic vocabulary of working with a graph, working with ordered pairs, working with equations in two variables. Hopefully this was enough to handle that. As always, thank you for joining me. I'll see you in the next video.